Hey everybody, these notes are going to be about black holes. And what you're seeing here is from 2019. This was the first ever direct image taken of a black hole. And it was done by linking telescopes from all over the world and synchronizing them to point directly at this area, uh, which was in a galaxy 55 million light years away. And the scientist behind that is this person. Now, I don't think I can play videos very well on this, especially with audio, but this is Dr. Bowman, and 29-year-old scientist who was able to come up with a way to stack all of the images from all of these telescopes from all over the world. Certainly quite the accomplishment by her and her team. So I'm just going to go ahead and try to play past this. I know on WeVideo, playing videos doesn't work very well. So I'm trying to, there we go. Okay, let's talk about stellar evolution real quick. And so we have two columns here. The left column are stars like our sun, sun-like stars, 0.4 solar masses to about 4 solar masses. Once again, they start their life in the main sequence. At the end of their life, they'll become a red giant, where they will fuse helium into carbon, nitrogen, and oxygen, after which they will become a white dwarf. They will run out of helium, they will lose their outer shell of material, and they'll be left with a very dense core. Slightly larger stars will go nova, which is a mini explosion of light as they lose their outer shell. Now let's take a look at stars greater than 8 solar masses. Once again, they begin their lives in the main sequence. When they use up their material, they will become a supergiant star. And as they become a supergiant star, that's when they fuse elements all the way up to iron, which is Fe on the periodic table. Once iron is created, they cannot continue, and the star collapses very rapidly and then explodes in what's called a supernova. After the supernova, the core will collapse into what's called a neutron star. Remember, a neutron star is like if you took all the space in an atom, all the electrons, and shoved them into the nucleus, all that space then is gone, and it becomes so dense that, they say a teaspoon of a neutron star weighs as much as Mount Everest or something like that. Now, I'm not going to, like I said, play this video on here, but formation of elements after the Big Bang, this goes into the idea that at the Big Bang, when we look far enough back in time, the elements formed after the Big Bang, of course, would be the simplest elements. As matter condensed from energy, the first things to form would have been protons and neutrons and electrons. And those came together, as well as their negative counterparts, but like antimatter and stuff like that formed. But let's just focus on the simple elements. When they came together, they would form the simplest elements. A proton and electron are pulled together through the electromagnetic forces, causing hydrogen to form. One proton surrounded by an electron. And that is how hydrogen is formed. And so most of the universe is hydrogen that was formed at the Big Bang. Some helium was formed, and also very small amounts of lithium, number 3 on the periodic table, were formed. Heavier elements are formed in stars. This graphic shows, across the bottom, I'll move this if I can. There we go. If we look at the mass of stars, main sequence stars, a mass similar to our sun, which is 1 solar mass, becomes a giant. Helium flash occurs, possible planetary nebulae forming a white dwarf, whereas stars larger than our sun follow this path. And we've gone over that, I think, plenty. Okay. So remember neutron stars. These are stars with less than 1.4 solar masses. Those become white dwarfs. This is what's called the Chandrasekhar limit. The Chandrasekhar limit is that size of a star, where if a star is larger than that, it will then become a neutron star. So 1.4 solar masses and less become white dwarfs. More than 1.4 solar masses will become neutron stars. So these objects are massive enough to continue collapsing. The pressure is so high that electrons and protons are fused together to form stable neutrons that fill the object. And that is where a star will collapse, basically the size of Burnsville. Okay, 10 kilometers or 6 miles in diameter. And the density will greatly increase because you're getting rid of all that space. That little point at the bottom, 1 teaspoon of a neutron star weighs around 100 million tons. And that's a fact. That's a true thing. That is because there is no empty space. Let's talk about escape velocity. All right, so everything has an escape velocity, right? It's the speed that something has to travel in order to break free of the gravitational force or leave the gravitational well caused by an object in space. You have an escape velocity because you have gravity, but it's so small that's undetectable. On Earth, well, you have to go about 25,000 miles an hour to leave Earth. The space shuttle, that picture shown here on the right, they don't launch them anymore. It went approximately 17,500 miles an hour. And so it was always still within the gravitational well of the Earth. Whereas when astronauts went to the moon in the late 1960s and early 1970s, those Saturn V rockets were able to go 25,000 miles an hour. And so that's 11 kilometers per second or 40,000 kilometers per hour. Okay, so gravitational force decreases with distance. It's that inverse square law again. So if you're twice as far away from an object, you have 1/4 the gravitational attraction. 3 times as far, you have 1/9, and so on. So the higher you are, the farther you are away from the center of gravity of an object, the less gravity you are feeling. So if you are on Mount Everest, it's actually a lower escape velocity than somebody in Minnesota, Michigan, or closer to kind of the center of the Earth, Death Valley, which has the lowest elevation in the United States, I believe. So if you're on the International Space Station, you need a lower escape velocity because you're farther from the center of the Earth. Now, they're only up 300 miles roughly, so it's not a huge difference as you might think. Ways to increase escape velocity. If you increase the mass of an object that you're on, the escape velocity is greater. So the Earth has a greater escape velocity than the Moon. And then something larger than the Earth, like Jupiter, doesn't really have a surface, but Jupiter, if you're trying to leave Jupiter's gravitational well, you would need a much greater escape velocity than you would on Earth. Or you can keep the mass the same, but increase the density. You can shrink an object down. Now, you'd also have to be on the surface of that object, so you'd have to kind of go down with it, but its escape velocity would actually be increased. Now, there's a point at which an object can be shrunk where the escape velocity reaches the speed of light. This is a term called the Schwarzschild radius. All right, so you could determine how big would the Earth have to be compressed down into in order to become, essentially what they're talking about here is a black hole, a point at which there's so much gravity, the escape velocity would be so great that light itself could not escape. And so we could actually calculate what the Schwarzschild radius would be for the Earth. That is when it becomes a black hole. So neutron stars larger than 3 solar masses don't stop shrinking. The radius eventually reaches the Schwarzschild radius, and then everything is stuck there. That's what forms a black hole. Inside of this point, the escape velocity is greater than the speed of light. Nothing can go faster than the speed of light, so nothing escapes. Now, the boundary at which this occurs is called the event horizon. Think of that as the point of no return. That is where the escape velocity is such that light cannot escape. And that's basically the boundary of the black hole. So neutron stars like this that keep shrinking, they become infinitely small, a singular point with an infinite mass, and those are referred to as a singularity. Now, this graphic, you can see the point, the center is a singularity. Here's the radius of the black hole, and then the event horizon is that point of no return. Well, so how can we see black holes? Light cannot escape them. Well, they form from neutron stars, and neutron stars are the leftover core of a supernova, so we can look for supernova remnants with no visible core, and that could indicate that there's a black hole inside. Most stars are binary, they come in pairs, so if you have a star that appears to be orbiting something that's not there, that thing that is orbiting may be a black hole, and that does occur. The first black hole, Cygnus X1, was actually discovered this way by Stephen Hawking. He had a bet with another physicist whose name escapes me right now about it being a black hole. So there's Cygnus X1 listed in black hole candidates. And like I said, that was the first one. There's a whole bunch more listed. Most galaxies are thought to have a supermassive black hole in their center, including the Milky Way galaxy. They can be hundreds to billions of solar masses. These are huge, probably essential for the structure of the universe, for the formation of galaxies. Black holes are probably more important than we realize for this. So if you were wanting to look for the black hole, the center of the Milky Way, you would look toward the constellation Sagittarius. So what are the properties of black holes? The matter forming a black hole loses almost all of its properties. The main properties of black hole would be the angular momentum, how fast it's spinning, its mass, and its electric charge if it's emitting radiation. Black holes are spherical, okay? I know we try to show them as kind of a hole in space, but that's just our way of trying to figure out, try to model them a little bit better. Outside the event horizon, Kepler's and Newton's laws all work just fine. The Earth could orbit a black hole. Not everything is sucked into a black hole. It still has a certain amount of gravity, and you can certainly orbit a black hole. But once you cross the event horizon, everything goes crazy. Our physics kind of break down there. Einstein was not the first to theorize about the existence of black holes, but he was one of the few to try to explain how they might work. According to Einstein, objects with mass create extra space, right? They bend space. If you look at a stick with the same diameter as the sun and if you took a stick the same diameter as the sun and stuck it into the sun, it would go all the way through. It wouldn't go all the way through. The objects with mass distort or curve space, so they actually create extra space. As you approach the speed of light, your mass increases, approaching infinite mass if you're trying to go the speed of light. So black holes then are considered to have infinite mass. Their acceleration is that it has infinite mass, and acceleration due to gravity. So black holes infinitely curve space-time. They can be described as forming an infinitely deep gravity well. And so what this is showing is little gravity wells. There's Venus, Earth, and so on. Jupiter's gravity well, Saturn, Uranus, and Neptune, and all that stuff. So a black hole would be infinitely deep. Some strange things about black holes. The gravitational redshift, so gravity can affect light, right? Light follows along the curvature of space. So light near the event horizon will be stretched out by the gravity of the black hole. And the frequencies of light would be lowered as well because it's getting so stretched out. Time dilation. The faster you go, the more time slows down. This has been shown with accurate clocks that are placed in space and on Earth and compared. So as you approach the speed of light, time slows to a stop. So once you reach the event horizon, you are moving infinitely fast. Time, though, has stopped for you. To an outside observer, you're frozen in time. And for you, you'd be able to see the entire history of the universe go by in an instant. You'd be able to watch that happen because your time, according to you, is going fine, but everything outside of your time, outside of the black hole, since yours has slowed down, but to your observation, you can't tell it's going normal for you. As you looked outside of the black hole, you'd see the entire history of the universe pass by you very quickly in front of your eyes. What happens if you jump in feet first? Well, you're not squished immediately. You end up getting what's called spaghettified. As you approach the event horizon, your velocity increases, so you start going faster. At your feet first, you get what's called a gradient, a change in gravity. So your feet are pulled faster than your head, and every atom of your body is feeling a different acceleration. So all of your atoms get completely stretched out. You'd basically be pulled into a human spaghetti noodle, and the term is spaghettification. There's a couple of videos here that we can take a look at, just not in the Wii video, just because it really doesn't work well. Wibbly wobbly, timey wimey stuff. This is a reference to Doctor Who. Math predicts, but we can't observe, that two singularities should connect. Black holes create a hole in space-time called a wormhole. This is scientifically called an Einstein-Rosen bridge. The idea is that if you had a black hole somewhere in space, and you could curve space-time to connect with another black hole, that you could create a bridge through those. So you could actually, without having to travel tens or hundreds or millions of light years, you could simply cross this. And that's one theoretical way to travel large distances in space. So you could enter in one and exit somewhere else in the universe. There's also the multiverse theory, in which numerous different similar yet different universes exist, and black holes or wormholes might allow people to travel, or something to travel back and forth. Completely theoretical, of course. Okay, that is it for your black hole notes. I'm sure you have questions, and we'll continue hopefully learning some more about black holes.